Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were discussing about the Castiglione's theorem, and we have derived the expression for the strain energy for an elastic body, right. Now, today in this particular class, particular lecture, what we will do, we will be trying to find out the strain energy under different types of loading system. Okay. So, first we will talk about whatever loading system already we have covered in our discussion. So, strain energy, okay, due to torsion. Okay. So, already we know that what kind of stress, strain, okay, get developed during torsion. Now, if we consider, we are considering circular cross section cylinder member and isotropic material, elastic, linear elastic of course. So, all those things are applicable. So, if we consider that kind of elastic body and under twisting moment of the torsion, then basically your strain energy can be written as, if you recall whatever we have got, whatever we have got the expression in the last lecture, tau theta z gamma theta z dV, because only tau theta z will be existing, right, under torsion. You know that from our previous discussion when we talked about torsion, and we have seen that what are the different stresses get developed during torsion. So, tau theta z will be only the existing part in case of torsion. So, this is your strain energy expression. Okay. Now, if you recall gamma theta z can be written as tau theta z by z, where g is the shear modulus, and we know tau theta z is equal to mt r by I z, right, where mt is the twisting moment, r is the radius, okay, and I z is the polar moment of inertia. Already we have derived all those things. So, now we will be putting that thing in this particular equation. So, therefore, I can write u equal to half 1 by g. Okay. So, so tau, instead of tau theta z, instead of gamma theta z, we can put tau theta z by g, and tau theta z is this. So, I can simply write 1 by g into mt r by I z dV, right, and this can be further written as half integration over the length L, okay, mt square by g I z square, okay, and over the area, integration over the area. So, that is basically triple integration, right. First integration over the length and then integration over the area, and that will be creating the integration over the volume. So, that is triple integration that you know. So, this I can write r square dA. So, this is your say dx or the dz, right. So, we are considering the z direction along the axis of the cylinder member. Okay. So, from what is this r square dA over the area A, that is nothing but the polar moment of inertia. So, that will be your I z, this will be your I z. So, I can simply write this half u equal to half mt square by g I z, okay, dz. That is the expression for your strain energy due to torsion. Okay. If you know MT square, if you know MT, that is the how much twisting moment is applied, if you know the shear modulus, if you know the polar moment of inertia, okay, you can find out the strain energy. Agreed? Okay. Now, we will be talking about strain energy due to bending. So, first we will talk about strain energy only due to pure bending, okay, and then we will be talking about strain energy due to bending as well as shear if they are acting. So, strain energy due to bending. Okay. So, in pure bending, okay, the total strain energy. So, first we will talk about in pure bending, the total strain energy U can be written as half triple integration as we were discussing that thing. So, that is basically over the volume that we can separate in triple integration sigma x epsilon x dx dy dz. Okay. So, this can be written as triple integration sigma x square by twice E dx dy dz, because you know epsilon x is nothing but sigma x by E. Okay. So, from here I can write 1 by 2 E. Now, what was the expression for sigma x in pure bending? If you recall, mb y by izz, where mb was the bending moment, y was the distance from the neutral axis, and izz was the moment of inertia, right, of the cross section, square, okay, dx dy dz. This can be further written as u equal to integration over the length L mb square by 2 E I zz square, okay, dx, and double integration, and we can simply write integration over the area A y square dA, where dy dz is nothing but dA. Okay, we can write down. Now, what is this? Simply izz, right. So, we can write down this as u equal to mb square by 2 E I zz dx. So, that is the expression for your strain energy under pure bending. Agreed? Any doubt? I hope everything is clear, right. I mean, we are just following the expression, or we are just following the steps involved in determining the strain energy. Now, if you want to find out the strain energy for both bending and shear, for both bending and shear, the strain energy will be u half triple integration sigma x epsilon x plus tau xy gamma xy, then the shear stress and shear strain will be also existing into dx dy dz. Okay. So, from this I can simply write triple integration sigma x square, if I take the first part, by twice E dx dy dz plus triple integration tau xy square by twice g is the shear modulus dx dy dz. Fine. Now, what is this? Just now we have got it, right? Strain energy due to only bending, and this is the part strain energy due to shear. Okay. So, that is basically the summation of the strain energies coming from bending as well as from shear. Okay. Now, basically it has been observed in different problems means the problems associated with the slender member under bending, where bending and shear both are present. There it has been observed that this US is very negligible as compared to UB. So, for slender member, the contribution of US is almost always negligible in comparison with UB. Okay. Therefore, it is common practice hence it is common practice to neglect the contribution to the strain energy due to the transverse shear stress. Understood? So, now onward, whenever we will be dealing with the slender member under bending, where shear force is also present, but this strain energy due to that shear force, that is US, is very negligible as compared to your UB. So, therefore, we generally almost in almost all cases we neglect this US. So, only we consider UB. So, therefore, if I want to analyze a slender member under bending as well as shear, so we will be considering only the strain energy only caused by this bending. We will not consider this part. This is very negligible as compared to this. Okay, fine. So, now if I want to collate all those things whatever we have learned so far, if I want to collate that if a slender member, okay, carries a tensile force, a force, axial force Fx, okay, a twisting moment say mt, okay, along x axis, say we are considering with respect to x axis, okay, and a bending moment say mb x, then the total strain energy of the system will be, if all the things are present, we have got one by one, right, when the axial force is there, when the torsion is there, when the bending moment is there. Now, if we have all the things, all types of loading, okay, on a particular slender member, then we can get the strain energy will be the addition of all L F square twice AE dx, okay, along x direction. Okay. So, the slender member is along x direction and the loading is also along with respect to x axis, and then this will be L mt square by twice g I x. We are considering x with respect to x axis. So, that is why we are writing I x, okay, d x, but that is nothing but the polar moment inertia with respect to x axis, fine. And then m b square 2 E I z z dx, right. That means, if you have this kind of system, this is one slender member, x, y and z axis, okay. You have along this f x, along this m t, and along this okay. If this kind of all the loadings, I mean all types of loading are present, then the strain energy can be written as this, okay. So, this f x, I mean I have written x here, this is not a function, right. F x, f means f is a constant, this is along x axis. So, that is why I have shown here like that. So, do not get confused with that, this is not the function of x, okay. I mean this is not as per our mathematical notation, this is not the function, rather this is the axial force along x direction, this is the twisting moment with respect to x axis, and this is the bending moment, okay. Well, so now we will take one simple example to understand this this Castiglione's theorem, how we can apply this Castiglione's theorem to find out the deflection. Very simple problem we will be taking. One simply supported beam with a central load P at point C. This length is L by 2, this is L by 2, total length is L. Now, we need to find out delta C. That means, at point C, what is the deflection under this kind of loading, and this is a slender member, and this will be carrying both bending and shear, and as per our previous discussion we will not be considering the strain energy contribution due to shear. So, only the strain energy due to bending will be considering. Okay. Now, before that we need to find out the support reaction, that is the initial job R A R B. So, this is your A, this is your B, say R A will be P by 2 symmetric loading, okay. This is also P by 2. So, now as per our previous knowledge, I can get two sections, okay, and then I can find out for section 1 okay, that means that is 0 to L by 2 okay. So, there your bending moment is, you know how to find out that, I am not P by 2 into x, okay. Now, for section 2 which is nothing but L by 2 to L, okay, and we are considering the left hand side of section 2. So, therefore, I can write that also, you can find out M B is equal to P by 2 into x minus P into x minus L by 2. So, if I simplify this thing, this will be simply P by 2 into L minus x. So, this is the expression of bending moment for section 1, this is the expression for bending moment for section 2. Now, if we add the strain energy for, if I want to find out the strain energy for section 1, I can find out because bending moment is known to me. I can find out the strain energy for section 2 that means this part from C to B, that strain energy, and then if I add them together that will give me the total strain energy of the whole system from A to B. Okay. So, now your delta C, that is our objective, delta C will be equal to, as you know, mB by EI, okay, del mB del P dx. Now, how it has come? Can you tell me? Because I know your U is equal to mB square by twice EI, okay, into dx. If you recall, right, mB square by twice EI into dx, that was your strain energy expression for bending moment. Now, to find out delta C, what you have to do? So, delta C is nothing but del U del P, because at point C you want to find out the deflection, and at point C you have the concentrated force P. So, as per your Castiglione's theorem, your delta C should be written as del U del P. So, del U del P is nothing but mB by EI del mB del P dx, that I have written here. Got it? Very simple. Now, you know mB for different parts. So, different parts means from A to C and from C to B you know mB. So, we are just writing down EI is constant. So, we are taking it out. Now, 0 to L by 2, which will define from A to C. What is the value of mB? P by 2x, and del mB del P if I do, that will be x by 2 dx, plus, now we are talking about from C to B, this part CB part, okay, 1 by EI L by 2 to L, okay. What is the value of mB? P by 2 into L minus x, P by 2 into L minus x, and what is the value of del mB del P? L minus x by 2. So, L minus x by 2 dx. So, if you do this integration, we getting delta C equal to PL cube by 96 EI plus PL cube by 96 EI. So, this part will be giving you this part will be giving you this. So, finally, you will be getting PL cube by 48. Yeah. You can verify with your previous solution, right. So, now you see very simply we have got the solution for delta C. If you, I mean, you can solve this problem, the same problem, using your double integration method, using your method of superposition, whatever you want, but this is another method by which you can easily find out the deflection, right. Now, here the main difficulty is that how to find out the strain energy, or I mean, if once you know the strain energy and once you know this is the expression for your delta C, then only this is a matter of concern that how you will find out your bending moment for different sections. Okay. So, I will stop here today. In the next class, next lecture, basically we will be taking another example, very typical example, okay, to find out or to determine the deflection by using your Castiglione's theorem, and then we will move to the next and the last chapter. Thank you very much.